Now that we've implemented our insertion method, let's go ahead and take a look at the modifications we need to do to the removal function in order to fully implement our treap data structure. If you recall, with our insert method, our deletion method is going to be very similar to our standard binary search tree implementation, with the main difference being the case when the node we want to remove actually has two children. In the binary search tree, we just find the smallest or the largest subchild and then effectively swap the two nodes, with the whole idea being that a node with no children is the simplest one to remove from the tree. We're going to be doing effectively the same thing with our treeps, but we're going to be going about it in a little bit different manner. So in our case, if we look at our just little mini subtree here, and let's say we want to delete node 15, right? In this case, we know that our node we want to delete has two children. So what we need to do is kind of take a multi-step process, with the first step being the removal of this node's normal priority. So here we basically want to remove this 100 and we're going to replace it with effectively negative infinity, right? In our code, this could be any extremely small number. Here we're using negative infinity as we're dealing with a max heap. The general idea being here that we want to force this node to move down the tree until it is a leaf node so that it can be easily removed. So after we've gone ahead and changed the priority of our node to be negative infinity, we now need to determine effectively which way we need to rotate our tree. Remembering rotations is effectively how we're going to percolate nodes and move them around our binary search tree /heap /treap, etc. So how do we determine which way to rotate? In other cases we've looked at, there's only been one node, so it was easy to determine the rotation. In this case, we just simply look at our children and we determine which one has the higher priority. In this case, our 10 node has a priority of 95, which is higher than the priority of our 20 node. So what we need to do is move 10 to the location where 15 originally was, and we can do this by rotating right. Alright, so we're going to go this way. So after that rotation, we go ahead and we'll have something that looks closer to this. So we have a node with our 10 and our 95, and then we have our 15 with negative infinity, and then we have our 20 and our 87. Alright, so we went ahead and we did our rotation, but our tree still isn't correct. 15 is still in the middle of the tree, and it's not necessarily the easiest thing to remove yet. Though in most cases we could remove this pretty easily just following our standard binary search tree rules, but if we wanted to take it a step further, we could go ahead and do another rotation yet again. So we would go ahead and do our same checks to determine if our heap property is being violated right now, which it is, because 87 is larger than negative infinity. So we would again apply yet another tree rotation. And in this case, it would be a rotate to the left, because we want to put 20 where 15 currently is, and it's the right child of 15. So after that tree rotation, we would basically end up with 10 with a right child of 20, and then 15 would become the left child of 20. And then after this tree has been constructed, we can very easily delete 15 from the data structure. as it has no children. So I at least personally think it's kind of cool how we can use these rotations to move a node down the tree, all the while enforcing our heap property as well as maintaining our binary search tree ordering. Note that as we moved everything here, we still have a technically valid binary search tree at every level. Right here, 15, 10 is smaller than 15, 20 is bigger than 15, 15 is bigger than 10, so this ordering's still right. 20 is bigger than 15, so that's still right. And after we rotated yet again, 20 is bigger than 10, 15 is smaller than 20, so all of our rules were still correct and everything was still enforced as it is supposed to be. So let's go ahead and take a look at how the code looks. So just like as in insert, most of our code is actually going to remain the same, with the only case we actually need to deal with being the case where a parent has two children, with the parent being the one we want to remove. So here, we'll come into our case that handles that, and the first thing we need to do is we will go ahead and change the priority of the node we want to remove such that it's always pushed down the tree. So for us, we're just going to do leaf arrow treap prio equals negative 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll just give it some, or that's going to be too big, some arbitrarily very small number such that it's always pushed down. After we've done that, we can go ahead and check to see which of its children has the higher priority and where it should be moved to, or which way we need to rotate this subtree. So to do that, we just get the children and we check their priorities. So if leaf arrow get left is get left arrow treap prio is smaller than leaf arrow get right treap prio, then we know that we are going to want to go ahead and rotate the tree right. Or I'm sorry, yes, that we want to rotate the tree right because the right node or the right child is larger or has a higher priority than its sibling. So again, to do that, all you need to do is leaf equals rotate, or I am very sorry. I keep getting my directions messed up. Even I mess this up sometimes. In the case that the left child is smaller or has a lower priority than its sibling, which is on the right side, we actually want to rotate everything to the left. This is why drawing things out can help things so much. So in this case, let's just imagine that this was 187 instead of 87. We want to replace our leaf node with its right child, and in order to do that, you need to rotate to the left. So leaf is going to equal rotate left around leaf. And then in order to continue things, right, because as we saw here, the node we want to delete may not have been moved all the way down to the bottom, we need to go ahead and call another recursive version of this function again, right? So we do leaf arrow set left, remove helper, the node we want to remove, and where to remove it from, which is the left subtree that we just pushed it down. Otherwise, if not for that, we would do else. We're going to rotate around the right. And then we will do the same thing by calling our recursive function again. mess this up here. Get right. All right, not get right, get left. So again, what's effectively happening here is we check to see which of the two nodes has the higher priority. And once we know, we call the correct rotation function. And when we rotate it, we effectively push the node down the tree, right? So at this first check, we have a tree that looks like our top tree after we call our rotate function, which in our case would actually be a rotate right. So after we call our rotate right, we end up with this, right? Where we've pushed the node we want to delete down the tree, and because it has not made it all the way down the tree, we again call our recursive function, right? Which will bring us to a new frame, and we can again try to remove the node from the tree, which in this case, we'd be able to just go ahead and delete it. But if you wanted to, you could force it to go all the way down as well. So this is all you need to do to implement the remove function for a treap. Now, the code is not that complex, but some of these operations are subtly complex and may take a little bit of thinking. And what can really help again with a lot of this is just taking the code line by line and kind of drawing out all the steps. But if you're getting mixed up or confused about any of these, please reach out to me so that we can go ahead and talk over what's going on and hopefully get you steered down the right track with it. So now that we've written all this code, let's go ahead and try to build this and see how many errors I end up with. I'm sure I will end up with more than a couple because writing a whole bunch of code and then trying to compile it all at once is never a great idea, but hey, it's what we end up doing anyways. I'm also not in the right directory here. Oh yeah, I am. So we'll go in source and let's try to make it. I forgot to modify the make file. Told you it wasn't going to go perfect the first time. We need to change this to treap. And then I'm also going to change the name of the output file right away. Okay, this time, it almost built. Treap.hpp, line 6. Oops, that's not the right file. Line 6. In file included from main, or sorry, line 147. Return new n. I don't want to do that. I just want to return n. Let's try this again. Make. Hey, it built this time. So remember when we ran our binary search tree version, BSC I don't want to CD either. bst.out, command.txt. When we ran this, we ended up with a height of 13. Let's see what happens when we run our treap with the same input file. As you can see here, we ended up with a height of 5, which is significantly better than a height of 13, simply because of how we are forcing the rotations and causing the tree to rearrange itself as we go. And if you want effectively proof that all of the tree orderings are being held correctly, you can check the in-order traversal and note that the numbers are still coming out in the correct order. So this means that the binary tree structure is still being enforced and all of the data is still in the right place. All we ended up doing was rearranging the tree in such a way that we could compact it down and create a much more efficient data structure than if we just had a effectively linear linked list. right? Which neglects or not neglects, boy, I can't word right now, but removes the benefit of having a binary search tree at all, right? So hopefully, this code was kind of useful and kind of interesting and kind of showed you how easy it is to build a more efficient data structure by just implementing a few rules, which can really help us create some very compact, efficient code. If you have any questions, again, please don't hesitate to reach out to me. And if you would like any of this source code to kind of play around with it, just let me know. I can send it your way. So with that, we will see you in the next set of videos.